All right, let's pull back the curtain on something that millions of us use every single day, but almost nobody really understands: the Twitter timeline. You know the feeling, right? You pop open the app, you give it a scroll, and new tweets just appear. It feels so simple, almost like magic. But behind that incredibly smooth experience is a monster of an engineering challenge. So, how does it actually work? And how on earth does it do it so fast? Well, first things first, we have to completely shatter a core assumption. According to the people who built it, the timeline is not just a simple, chronological list of tweets. Not even close. It's better to think of it as an economic system that's constantly deciding where and when to spend its computational budget. Thinking it's just a data problem misses the entire point. At the very heart of this entire thing is one fundamental choice. It's a classic engineering trade-off that dictates pretty much everything else. Do you push content out to your users, or do you have them pull it whenever they're ready? This brings us to a key concept called feed materialization. Now, that sounds a little technical, but the idea is simple. Who pays the computational price? Do we pay it all up front the second someone hits post, or do we pay it on demand only when you refresh your feed? This single decision has massive, and I mean massive consequences. So let's look at the two pure ways you could do this. On the left, we've got the push model, or fan out on right. When you tweet, the system immediately goes out, finds all of your followers, and stuffs that tweet into each of their timelines. All the hard work is done at right time. On the right, we have the pull model, fan out on read. In this world, when you want to see your timeline, the system scrambles to find everyone you follow, grabs all their latest stuff, and builds your feed right there on the fly. All the work happens at read time. And this table here just lays out those choices perfectly. With push, you can see the right cost is really high. It gets more expensive the more followers you have. But the read cost, it's practically zero. That's why your timeline would load instantly. Now with pull, it's the complete opposite. Posting is cheap and easy, but reading your timeline, well, that's where you pay the price. It's expensive, and the load time can be all over the place. So you're probably thinking, okay, push seems way better for the user, right? Timelines are fast. And you'd be right, until you slam headfirst into the single biggest reality of how social networks actually work. The thing is, social graphs are incredibly lopsided. They follow something called a power law, which is just a fancy way of saying that most of us have a pretty normal number of followers, but a tiny, tiny fraction of users, celebrities, news outlets, you know the type, have millions. This isn't just some minor detail. This is the whole problem. And this visual just drives home the scale of it all. A single user posts one tweet, and that one action might need to be delivered to 31 million individual timelines. The amount of fan out from that one click is just enormous. Just let that number sink in for a second. 31 million. Can you imagine trying to do 31 million database writes in just a few seconds, all because one person sent one tweet? And here's the key architectural insight: that celebrity user is not an edge case. They are the main problem. They are the dominant scaling constraint. If you try to use a pure push model, you'd create what are called write amplification storms, these massive cascades of writes that would literally melt the servers. It's just not possible. So, if pure push doesn't work and pure pull has its own issues, what do you do? Well, this is where the engineers got really creative. They didn't choose one or the other. They built a system that cleverly uses both. The solution is this really elegant three-part hybrid strategy. First, for the vast majority of us, they use the push model. This keeps timelines feeling fast and fresh. Second, for the celebrities, they totally switch gears and use the pull model to avoid those system-crushing write storms. And third, they cache everything they possibly can. Caching acts like a giant shock absorber, soaking up load and preventing the system from redoing the same work over and over. So here's how it actually works. The system's first job is to classify every single user. Are you normal, or are you a celebrity? When a normal user tweets, it goes down the push path. A fan-out service just zips that tweet into their followers' timelines. But when a celebrity tweets, nothing gets pushed. Instead, when you open your app to see your timeline, the system says, oh, hey, I also need to go grab the latest from that celebrity, and it pulls their tweets in on demand, mixing them into your feed. Two completely different paths for two different types of users. And this really is the core principle of it all. You can't build a feed system that scales by treating everyone the same. It's impossible. The only way to survive that power law is to classify your users and treat them differently based on their potential to wreak havoc on the system. But, that's how it works on a good day. What happens when things inevitably go wrong? A truly robust system isn't just about handling scale when things are sunny, it's about how it behaves when parts of it start failing. And this table here shows how they actually plan for things to break without the whole system falling apart. Like if that fan out service starts getting slow, your timeline just gets a little bit stale. You probably wouldn't even notice. But what if the whole timeline database goes down? The system just cleverly falls back to pulling everything on read for everyone. Yeah, it's way slower, but it still works. The service stays up. And all of this points to a core design philosophy. The system is built to degrade gracefully, not catastrophically. It will always choose to show you something, even if it's a little old or incomplete, rather than just show you an error page. For a system at this scale, being available is almost always more important than being perfectly up to the millisecond fresh. Okay, so let's zoom all the way out and lock in the most important takeaway from this whole thing. How should you think about systems like this in the future? Let's start with what not to do. There's a really common and dangerous trap in system design, which is this idea that you should treat all users the same. It sounds noble, right? Pure, elegant, but in a system with this much skew, it is a recipe for absolute disaster. The correct way to do it is the exact opposite. You have to design for the skew. You have to build your system around the outliers, the celebrities, because their behavior is what will break everything else. In these feed systems, the 1% literally define the architecture for the other 99%. And that brings us right back to our final core mental model. A feed isn't just a technical problem, it's an economic one. Every single design choice is just an answer to a simple question. Who pays the computational cost and when do they pay it? Do you make the writer pay or the reader? Do you pay now or do you pay later? Thinking this way really changes how you look at the digital world. So I'll just leave you with this question to chew on. What other systems that you use every day, from e-commerce sites to search engines, are secretly being defined not by the average user, but by their most extreme outliers?